Welcome to clickmeprojects.com. Device authentication is an important issue in cryptography. An authority which approves devices for use scopes to be able to distinguish authentic devices from fake copies which are not licensed for use. Conventional methods for dealing with this problem require each device to store a secret unique key in non-volatile memory on the chip and the use of cryptographic algorithm to encrypt and protect confidential information. This method is ineffective when it comes to devices such as RFIDs, which are highly resources constrained, thus not able to implement cryptography at low cost. Besides, managing these secrets in non-volatile memory is difficult and expensive. Physical unclonable functions can be used to realize device authentication at low cost. They utilize the manufacturing variations on each chip to create a secret that can never leave that chip. Generally, a PUF takes an m-bits challenge and generates an n-bit response. This response varies from chip to chip in a and random manner, though each chip has an identical implementation of the same PUF design. Manufacturing various cause that the challenge response mapping is unique to each chip. Hence, each chip can be uniquely authenticated. A trusted party stores a certain amount of randomly chosen static challenge and response pairs in a secret database when it possesses authentic chips. Several schemes can be proposed to implement PUFs. Some PUFs explicitly introduces randomness while other makes use of intrinsic randomness. The former group includes optic PUF and protective coating based PUF. The latter group includes silicon PUF, SRAM PUF, butterfly PUF, and tri-stated buffer based PUF. Another silicon PUF implements a ring oscillator based PUF. These PUF implementation methods derive their PUF behavior from delay variations of gates and wires, while other researchers also studied new possible applications for PUFs, example IP protection. This paper focuses on the ring oscillator PUF, which pointed out a ring oscillator based PUF in more FPGA friendly and can be integrated with an ring oscillator based random number generator. Now I am going to explain flow diagram of a project. In the first stage, we initialize the ID by giving the initial values as set any other 8-bit data. Then this was fed back to the ring oscillator. In the ring oscillator, it checks for each and every iterations and provides a random numbers which are providing by using the algorithms of entropy algorithm. After that, this will get the random bits for each and every RO cells. In the RO cells, there are 8x8 or 9x9 that's structures which are connected to the decoder stage. From the decoder stage, it extracts the addresses which are located from the particular row or column sizes. Because of these cells are arranged in a matrix. Then from the decoder output, we check whether there are significant changes or not for each every random number generation cells. Then this was given to reinitialize the values of system ID. Then finally we extract the multiplexer output as a random ID generation for each systems in the SOC. Now I am going to explain running procedure of our project. In the first stage, we extract the check syntax error and display the audio schematic diagrams and technology schematic diagrams. In this case, select the implementation option and select main function. Then select the check syntax in synthesis exhaustive and right click it and press run option. This will display any errors and warnings which are provided in the code. Then after that, we display the audio schematic diagram by right click it and press run option. This audio schematic diagrams displays the logical diagrams which are implemented in the codings. This displays the overall architecture designs which are provided in the coding. Press add and press create schematic. This is our overall schematic diagram. In this case, the inputs are click, enable and reset. Output is the orange output. We can view the internal structure by right click it. This is our overall schematic diagrams of concept. Now we can view the technology schematic diagram by right click it and press run option. Press add and create schematic. This is our internal architectures of the technology schematic. This will display the LUTs and flip-flop architectures and in buffer domain. Now I explain the timing diagrams which are presented in the page spectrum. Now select the option simulation. Then select main function and run the simulated neural model. In this case, we display the timing diagrams which are presented in the paper. Here we are using iSim simulator to display the timing details of the implemented result. The run clock. Initially, clock input is set to 0 and reset condition is set to 1. Enable is set to 1. And press run for the time specified on the toolbar. After that, use the input clock pulse as 1 and press run option. In this case, the total overall chip will be reset. Now change the reset condition set to 0. Now clock input is set also 0. Now press run option. After change the clock pulses at positive edge, a random number will be generated. For each and every iterations, when we change the clock cycle, random numbers will be generated. This will generate the random IPs. So provided to the internal chip. This is our final output, random number generator. These IDs are provided to each and every chips which are provided to it. Thank you.